Welcome to the journey of science and sleep, where curiosity is nurtured in a peaceful atmosphere. Imagine gently letting your mind drift in the quiet of the night as we explore the radiant secrets of the universe together. Tonight, our gaze will turn to one of the most spectacular phenomena in the sky: solar flares, the magnificent fireworks that our central star gifts to us. If you find this topic interesting, don't forget to subscribe and stay until the end of the video so you won't miss the moments that are both magical and guide you into a peaceful sleep. When we look up at the sky at sunrise or sunset, the soft golden light of the sun seems so familiar and peaceful that we might mistake it for a still, unchanging celestial body. But behind that dazzling radiance lies a completely different reality. The sun is a gigantic reactor, a living, turbulent sphere of plasma, where energy is constantly being born, twisted, and exploding outward into space like cosmic fireworks. Looking a little deeper, we will see that in the very heart of the sun, under pressure and temperature far beyond imagination, hydrogen atoms continuously collide and fuse into helium. This nuclear fusion process releases enormous energy, but that energy does not escape immediately. It takes thousands, even hundreds of thousands of years to gradually move from the core to the surface, passing through dense layers of plasma. When it finally escapes the surface, that energy becomes light and heat, warming our small blue planet. From that perspective alone, the sun seems like an eternal friend, silently nurturing life. Yet plasma is not an ordinary substance. It is a state of matter that conducts electricity extremely well, making the sun not just a ball of fire, but also a colossal magnetic energy mass. As plasma moves, it drags magnetic fields along, creating complex swirls, invisible strings bending and twisting across the surface. Like guitar strings pulled too tight, sometimes the magnetic field lines snap and reconnect, releasing an immense amount of energy. That is the moment of a solar flare. Imagine a tiny crack on frozen winter ice. Under pressure, the whole sheet can shatter. Similarly, when the sun's magnetic field lines break, energy stored for weeks or even months is unleashed in just a few minutes. A flash erupts billions of times stronger than nuclear bombs, blasting electromagnetic radiation straight into space. For astronauts or satellites, these are invisible yet dangerous storms. But for us on Earth, the consequences sometimes arrive in a breathtakingly beautiful form: shimmering auroras painting the skies of both poles. These flares are not rare events. They occur in rhythm with the sun, tied to a cycle lasting about 11 years. During the cycle's peak, sunspots, regions where magnetic fields converge, appear densely, signaling intense flaring activity. At solar maximum, the sun resembles a flamboyant artist, constantly releasing symphonies of light and energy. Conversely, during solar minimum, sunspots become sparse and the surface looks calmer. But that is only a temporary stillness, like the sea before a storm. What is astonishing is that humanity has only truly understood these rhythms in the past few centuries. Since ancient times, people viewed the sun as a perfect disk of light, a symbol of eternity. Only with the invention of the telescope did the first sunspots reveal themselves, showing that this star is in constant flux. Those initial observations changed our entire perspective of the sun. No longer a changeless lamp, but a living, breathing celestial body with its own rhythm. Today, with modern telescopes and space probes, we can observe the sun in many wavelengths, from visible light, ultraviolet, to X-rays. Each wavelength opens a new world. If to the naked eye the sun is only a bright golden disk, then through ultraviolet lenses it appears as a forge of plasma with giant arcs bending into space. In X-ray images, flares blaze and spread like fleeting bursts of anger from a cosmic giant. But thanks to modern science, we also realize these phenomena are not just beautiful spectacles. They can directly affect everyday life. A strong flare, accompanied by the ejection of billions of tons of plasma, called a coronal mass ejection, CME, can trigger geomagnetic storms when reaching Earth. The result is potential disruptions to power grids, satellites, and even the internet. In 1859, the Carrington event, one of the strongest solar storms ever recorded, crippled telegraph systems worldwide, even causing fires at many stations. If a similar event were to occur in the digital age, the consequences would be unpredictable. However, alongside the threat, the sun also bestows a stunning gift: the aurora. When charged particles from flares collide with Earth's atmosphere, They illuminate the night sky with swirling bands of green, red, and purple. For many, this is proof that even chaos can create beauty. These natural fireworks remind us that the universe is not only a place of strict laws, but also a stage for wonders. Every solar flare, whether strong or weak, is a piece of a greater story, the story of a living star. The sun is not merely rising and setting to mark day and night. It is a dynamic entity, always changing, and that change shapes the world we live in. When sitting under the gentle golden light of morning, you may feel peace, but remember that above, a colossal dance of energy is unfolding, both dangerous and magnificent. To truly feel the power and richness of a solar flare, we must go beyond the limits of the naked eye and expand our vision to the entire electromagnetic spectrum. What our eyes see, the rainbow band of light from red to violet, is only a very small part of the vast cosmic symphony that the sun performs every second. From radio waves with wavelengths of kilometers to gamma rays carrying the highest energies, the sun emits it all, simultaneously, in a grand harmony of energy. Imagine the spectrum as a gigantic piece of music. Visible light is only a few notes in the middle of the orchestra, easy to hear and familiar. But around it are deep bass lines that the human ear can never perceive. Those are radio waves. At the very top are the piercingly strong notes, so bright they nearly tear through the silence. Those are X-rays and gamma rays. Each type of radiation tells a different part of the story of our star. Radio waves, for instance, were one of the first ways humans heard the sun. When a flare occurs, powerful radio signals can disrupt communications on Earth. In the mid-20th century, scientists first recorded strange noises in radio receivers, realizing they were not technical glitches but the echoes of a solar fire erupting 150 million kilometers away. The sun, it turns out, can sing, not with sound, but with electromagnetic waves. Higher in the spectrum, ultraviolet and X-rays tell us about the outermost layers of the sun's atmosphere, especially the corona. Here, energy from magnetic reconnection events is violently released, heating plasma to millions of degrees, glowing brightly in far ultraviolet and X-rays. When scientists point space telescopes toward the sun, the images captured are not of a gentle golden disk, but of a tangled network of glowing arcs, surging like luminous cracks on a colossal shell. Then come even higher energy rays, gamma rays. These are the pinnacle of cosmic violence, usually appearing only in the most powerful explosions. When a solar flare emits gamma rays, it is a sign that particles have been accelerated close to the speed of light, colliding and producing radiation so intense it exists only for an instant. Though they do not last, gamma rays are like powerful whispers from the star, proving that the sun can become a gigantic particle accelerator. Each part of the spectrum is like a doorway into a different layer of the sun. If visible light shows us a surface full of sunspots, then X-rays and ultraviolet reveal arcs of plasma. Radio waves expose the tremors in magnetic fields, and gamma rays reveal the extreme moments where energy is pushed to its limits. Put together, they form a panoramic picture. The sun is not an unchanging circle in the sky, but a symphony of energy, glowing across the entire cosmic orchestra. This also explains why scientists always need many different telescopes and satellites, each listening to a specific range of wavelengths. A telescope on Earth only shows us a small part, like sitting through a symphony, but only turning on the violins. But when instruments are added to capture radio, X-rays, ultraviolet, and gamma rays, the whole music becomes fuller, grander, and also much more complex. With this broader view, we begin to see that solar flares are not just isolated events. They are highlights in the never-ending music of the star. A sudden flash in X-rays, a radio echo spreading through space, a gamma ray flaring and fading, all are the rhythms of a beating heart. And that heart is what keeps us alive. But this music does not only echo in the distant void. It touches our planet in very real ways. Strong radio waves can disrupt communications. Ultraviolet and X-rays from a flare can ionize the atmosphere, causing shortwave blackouts for minutes. And when high-energy particles reach Earth, they strike the magnetosphere, sparking auroras but also posing risks to satellites, aircraft, and even ground power grids. It is strange to think that the same phenomenon can be the source of the most beautiful displays in the night sky and also a threat to modern digital civilization. That is the paradox of the sun. both life giver and harbinger of chaos. And perhaps what makes it all the more fascinating is the truth that we are only just beginning to understand this symphony. Every new satellite, every new telescope is like adding another instrument to the orchestra. The music is still playing with many passages we have never heard, never known, and perhaps someday soon, another flare will reveal a new melody, surprising us once more with this familiar yet mysterious companion. When speaking of solar flares, it is hard not to think of the consequences they cause on Earth, where we often believe ourselves separate, yet in reality are tied closely to every pulse of energy from our central star. A massive X class flare is not just a distant astronomical event, it is a violent gust capable of shaking the digital civilization humanity has built. The ionosphere, the upper layer of Earth's atmosphere, is like an invisible mirror reflecting radio waves. When intense radiation from a flare arrives, this mirror becomes distorted, causing high frequency radio waves to lose their path, leading to sudden silence on the bands that pilots, sailors, and explorers rely upon. These shocks do not last forever, but just a few minutes of disconnection in an emergency is enough to emphasize that the sun is not only a source of life, but also a source of challenge. The impacts do not stop at the ionosphere. When a flare is accompanied by a coronal mass ejection, vast clouds of plasma hurled into space, they can take several days to reach Earth. If they collide with the magnetosphere, the planet's magnetic shield, they create geomagnetic storms. In those moments, the whole planet seems to resonate with a tense chord, induced currents running through power lines, threatening overloads on the grid. GPS signals, dependent on nanosecond precision, become unstable, and satellites worth billions suddenly turn into vulnerable targets in a sea of high energy particles. A modern world dependent on electronics and information is suddenly exposed in its fragility before the wrath of the cosmos. Yet within these dangers lie some of the most enchanting spectacles. Auroras, the northern and southern lights, are the artworks the sun paints across the sky when charged particles flood into the atmosphere. Bands of green, red, and purple light move gracefully like giant silk ribbons. To our ancestors, they were divine omens. To modern science, they are vivid maps of how solar energy touches Earth. Each time the aurora flares brightly, we know that above us, in the invisible realm of space, a storm is raging. It is a beautiful reminder that threat and wonder sometimes walk hand in hand. History also records powerful evidence of this strength. In September 1859, one of the strongest solar storms ever known occurred, the Carrington event. At that time, electrical technology was only in its infancy, yet telegraph systems across Europe and North America burst into sparks, wires melted, and some machines continued to operate even when disconnected from power. Auroras glowed so brightly they were seen as far south as Cuba and Hawaii. If such an event were to occur in the age of satellites, global grids, and the internet, the consequences would be immeasurable. It is like a mirror showing that humankind, no matter how advanced, must remain humble before the power of the universe. Modern scientists not only record, but also strive to predict solar storms. Observatories such as SOHO, SDO, and the Parker Solar Probe constantly monitor the sun, collecting data from every ray of light, every particle of solar wind. They are learning to read the language of plasma and magnetic fields as if listening to music from a giant orchestra. Every plasma twist, every spike in X-rays is a signal foretelling what is to come. However, just like weather forecasting on Earth, predicting solar storms remains full of challenges. Some powerful flares do not head toward Earth, while some small ones cause unexpected effects. This makes the research not only a science, but also an art, blending physical theory with observational intuition. What is noteworthy is that studying solar flares not only helps protect Earth, but also opens doors to broader understanding of the universe. Mechanisms like magnetic reconnection or particle acceleration are not unique to the Sun. They occur in distant galaxies, in black hole jets, or in supernova explosions. By decoding a solar flare, we are also unlocking universal physical principles governing the cosmos. In that sense, the sun is not just a nearby star, but a vast laboratory before our eyes, where humanity can directly observe the fundamental laws of nature. Moreover, understanding solar flares has practical meaning for humanity's energy future. In fusion reactors, where we attempt to recreate the sun's power on Earth, plasma must also be controlled, held stable against its natural tendency toward chaos. Studies of how solar plasma reorganizes itself, how magnetic fields twist and erupt, are offering valuable lessons for the clean energy technology humanity hopes for. One could say that observing a flare is not only looking into the present, but also learning for the future. In all these aspects, from danger to grandeur, from satellite protection to dazzling auroras, there runs a single truth. The sun is never still. It is a colossal heart that never stops beating, sometimes gently, sometimes violently, but always with a rhythm that shapes the entire solar system. We, the small inhabitants of Earth, are both spectators in awe, direct witnesses, and at times victims of these cosmic fireworks. That is why studying, listening to, and respecting our star is not only a passion of science, but also a way to safeguard the very civilization we have built. When observing solar flares and coronal mass ejections, CMEs, we are not only looking at an isolated phenomenon. In fact, these are interconnected stories between light and darkness, between dry scientific data and concrete impacts on human life. Each eruption is like a chapter in the sun's massive diary, recording both stability and sudden fits of anger. And it is through recording and analyzing those chapters that humanity gains a deeper understanding of the fragile relationship between the blue planet and its mother star. One of the things that makes CMEs a particularly fascinating subject is the contrast in how we experience them. From the ground, many people only know of CMEs through the shimmering auroras spreading across the poles, like luminous silk curtains gracefully swaying in the sky. But for satellite operators, CMEs are not a dance, but a potential nightmare. Just one unexpected magnetic impact can disrupt control systems, interfere with communication signals, or in the worst case, destroy a satellite worth hundreds of millions of dollars. This contrast evokes both wonder and a reminder that the beauty of the universe always comes with a price. When we look at history, we see that those powerful bursts have left their mark on the course of science. The Carrington event of 1859, often mentioned, not only ignited telegraph wires, but also marked a new era in human awareness. For the first time, people understood that the star in the sky was not just a silent source of light, but a force capable of reaching into everyday life. That event was like a warning bell echoing through time. If in the 19th century damage was limited to telegraphs and a few small fires, then in the 21st century, when everything from airplanes, GPS to the internet depends on stable signals, the potential risks have multiplied many times over. Equally important, the August 1972 event, which occurred between two Apollo missions, revealed another aspect: the direct threat to astronauts' lives. It is difficult to imagine that if the launch had been delayed by only a few weeks, those space explorers would have faced radiation doses far beyond safety thresholds. That fortunate timing became a reminder that every step outside Earth's magnetic umbrella must face risks that cannot be underestimated. Thanks to such lessons, space agencies have established continuous solar monitoring procedures, treating space weather observation as no less important than Earth's weather forecasting. Meanwhile, modern technology has opened the front row seats for us to observe these massive eruptions. The SOHO, Stereo, or more recently the Parker Solar Probe have captured arcs of plasma like luminous waves erupting from the sun's surface. These images, when widely shared, not only delight the scientific community, but also inspire millions of astronomy enthusiasts. Through them, the public begins to see the truth. The sun is not a static sphere, but a dynamic world, where twisted magnetic fields burst into giant storms. This is an important step because only when the public is aware can we invest adequately in protecting infrastructure against cosmic threats. Beyond the scientific aspect, the classification of eruptions also carries a surprisingly human and relatable dimension. By assigning them labels like C, M, or X, humans have transformed the sun's unfathomable chaos into a system that can be understood, predicted, and prepared for. Behind a simple letter lies an entire story. About 2003, when a series of X-class flares lit up the night sky. Or about 2012, when the X 5.4 event reminded the world that the sun's calmness was only temporary. Thanks to this system, science not only manages data, but also conveys a profound message that the invisible, chaotic, can indeed be translated into a shared human language. Another fascinating aspect is the universality of these phenomena. What we learn from the sun, magnetic reconnection, particle acceleration, plasma expansion, can all be applied to understanding larger cosmic events, from black hole jets to supernova explosions. In other words, each time we study a CME, we are not only learning about Earth and the sun, but also touching on the fundamental physics that governs the universe. The sun, therefore, is not just our star, but also a vast natural laboratory where universal laws are revealed in real time. But all of this analysis, data, and forecasting ultimately brings us back to a simple truth. The sun is both a source of life and a challenge. It nourishes the planet with light, but it also tests civilization with electromagnetic storms. It paints magnificent auroras, but also threatens power grids and satellites. It is precisely this duality that makes the study of solar eruptions essential, because understanding them better not only helps us prepare for challenges, but also helps us appreciate the fragility of this small planet in the cosmic ocean. Solar storms, when viewed through the lens of science and culture, are not merely physical phenomena, but events that connect every aspect of human existence. We have just seen that auroras are a natural miracle born from charged particle collisions in the atmosphere, but that is only the shimmering outer shell. Inside, the story is far deeper. It is the fragile balance between the terrifying power of a star and the resilient endurance of a planet. When a CME strikes the magnetosphere, much of the energy is transformed into geomagnetic storms. It is the magnetic reconnection in near Earth space that opens the gate for energetic particles to rush downward. This image evokes a symphony. Magnetic field lines are like taut strings, and when a hammer of solar plasma strikes, the entire celestial orchestra immediately resonates. That sound does not reach the ears, but manifests as light in the sky and as invisible currents running through the ground. It is the moment when science merges with art, when physics turns into imagery and emotion. What is remarkable is that these phenomena do not occur only on Earth. Each planet in the solar system, depending on its magnetic field structure and atmosphere, has its own way of answering the sun. Jupiter, with a magnetic field 20,000 times stronger than Earth's, produces auroras so intense that astronomers can observe them with radio telescopes. Saturn has ethereal blue lights embracing its rings. Even Mars, though its global magnetic field has long vanished, still shows localized auroral spots over magnetized regions. This diversity reveals a truth. Solar storms are not only Earth's affair, but a common language of the entire solar system, where each planet translates the star's message in its own way. Returning to humanity, we see the influence of these storms permeating every layer of technology. We live in a world dependent on satellites, power grids, telecommunications, and aviation. If a geomagnetic storm as powerful as the Carrington event struck today, the consequences could begin with widespread GPS loss, leading to disruptions in air and sea transport, grid collapses across multiple nations, leaving hundreds of millions without electricity for weeks, and even interruptions to transoceanic fiber optic cables, disturbing the global internet. All these scenarios highlight the fragility of a digital civilization. Just a few minutes of the sun's anger could shake centuries of technological achievement. But on the other hand, these challenges have driven human progress. It is precisely the risks from space weather that have led NASA, ESA, and many other space agencies to invest heavily in early warning systems. The SOHO Observatory, ACE, and DS-COVR satellites not only record the solar wind, but also transmit real-time data to Earth, giving us tens of minutes of preparation before a CME arrives. In science, that brief window is enough to reorient satellites, temporarily power down sensitive equipment, or adjust grid operations to reduce damage. This is proof of adaptability. Instead of being helpless before the universe, humans learn to listen and prepare. It is also through studying solar storms that we gain a clearer understanding of planetary history. Many scientists believe that Mars' loss of a global magnetic field, leaving its atmosphere eroded by the solar wind, is the reason it became dry and cold as it is today. By contrast, Earth has been fortunate to retain its molten core, maintaining its invisible shield. Without this protection, life may never have arisen, or might have been extinguished early on. Thus, each solar storm not only gives us insight into the present, but also opens clues about the past and future of planets. All these elements make observing auroras and solar storms both a scientific and philosophical experience. The observer may admire the dazzling beauty in the sky while also recognizing their own fragility. When green and violet lights dance over the North Pole, it is not only a visual spectacle, but also the fingerprint of a cosmic storm that has just passed. It reminds us that Earth's peace is always tied to the sun's turbulence, a distant yet inseparable relationship. From a cultural perspective, it is no surprise that auroras and solar storms have illuminated human imagination for millennia. From Norse mythology with the Valkyries to Inuit beliefs that auroras are ancestral spirits playing or omens of war in medieval European culture, all reflect humanity's awe of phenomena beyond control. Today, science has explained the physical mechanisms behind them, but their mystical allure remains intact. This is the unique fusion, where reason and emotion coexist, where science does not diminish beauty but deepens it. Perhaps that is why, whenever a solar storm appears, it not only shakes technology but also stirs a rare sense of humility. In modern life, we often believe we control everything, from electricity to satellite signals. But just one gust of plasma from a star 150 million kilometers away is enough to prove that such control is only temporary. And that is the greatest lesson the sun leaves us, that our existence is bound to a vast universe where beauty and danger always go hand in hand. When looking at the aurora, we often only see a dazzling display across the night sky. But hidden behind each streak of light is an entire journey that begins in the heart of the sun. In its fiery core, where temperatures reach millions of degrees, nuclear reactions take place continuously, releasing immense energy in the form of light, heat, and charged particles. Some of these, through solar flares and coronal mass ejections, escape gravity and rush straight into interplanetary space. When these particles collide with Earth's magnetic field, the celestial play called aurora officially begins. What gives the aurora its strange allure is not only its shimmering colors, but also the feeling that it is alive, breathing. Waves of light roll, burst open, and dissolve, revealing an endless dance between the sun's plasma and Earth's magnetosphere. Each time we look up, we may see green silk-like ribbons, fiery red spots, or rare violet streaks shooting across the sky. No two moments are ever the same, because each gust of solar wind carries a different magnetic structure, creating a spectacle that is one of a kind. But the aurora is not only the art of the cosmos. It is also a scientific language, a mirror reflecting the intensity and characteristics of geomagnetic storms. When scientists observe the shape, color, and extent of the aurora, they can infer the level of energy Earth is receiving. In this way, the aurora becomes an important tool for studying space weather, a field that is becoming increasingly essential in today's technology-dependent world. Space weather, unlike the familiar rain and sunshine on the ground, consists of variations in solar radiation and wind. When a geomagnetic storm erupts, we see not only lights in the sky. Induced currents can surge through power grids, damaging transformers. Radiation can interfere with satellite navigation signals, and streams of high-energy particles can even threaten the health of astronauts working in space. In a way, the aurora resembles bright warning lights across the sky, reminding us of our fragile connection to the central star. One of the clearest examples of the sun's power is the Carrington event of 1859, when astronomer Richard Carrington happened to observe a flash of white light erupting on the sun's surface. He could not have imagined that just a few hours later, the entire planet would be shaken by one of the most powerful geomagnetic storms in history. The aurora flared so brightly that newspapers could be read at night, stretching from the polar regions down to tropical latitudes. Miners thought dawn had come early, and sailors in the Caribbean were astonished by colors never before seen in the southern sky. But that beauty came with chaos. Telegraph systems, the most advanced technology of the time, sparked, burned out, and went offline. In some places, telegraph equipment continued to work even after batteries had been disconnected, powered by the very induced currents from the storm flowing through the wires. It was the first time humanity realized that solar activity was not just a distant spectacle, but could directly affect infrastructure on Earth. If a similar Carrington event occurred today, the consequences would be far more unpredictable. Instead of just a few telegraph lines, we now have an entire civilization dependent on global power grids, navigation satellites, the internet, and billions of mobile devices. A geomagnetic pulse strong enough could cripple electrical grids across multiple nations, destroy massive transformers, and cause power outages lasting for months. Satellites could be disabled, leading to disruptions in GPS navigation, aviation communication, and even the global supply chain. What once only inconvenienced telegraphs could now shake the entire world economy. This is why modern scientists devote so much effort to forecasting space weather. Monitoring satellites placed at Lagrange points track each solar wind, sending early warnings to grid operators and aviation authorities. Researchers also search for traces of ancient storms in ice cores and tree rings, estimating the frequency of such rare events. All of this is to prepare for the possibility that another Carrington scale storm could happen again. Yet, alongside the concern, there remains an undeniable sense of wonder, because the aurora, though a sign of the sun's turmoil, appears in the sky as a gift of beauty. Standing in the snowy Arctic forest or on a ship's deck at sea, gazing up at the luminous, rippling bands of light, one feels a connection both intimate and vast. Charged particles born 93 million miles away, traveling through empty space, colliding with the atmosphere, finally become glowing ribbons stretched across the sky. It is the journey of energy, transformed from storm into beauty. Perhaps this is the deeper message the aurora conveys, that within the most violent processes, beauty can still be born. From chaos comes order, from danger comes wonder. And when we quietly watch those glowing curtains, we are not only witnessing science, but also hearing a whisper from the sun that this small planet is always part of the grand cosmic dance.